Casting techniques of architecturally developed forms have proved best effective when concrete is coupled with an exterior membrane that holds it into shape. Whether it's small urban installations or big maneuvers, a huge amount of waste are generated by this technique, especially if the mold is of single use. Which led us to think of a solution: b0t. b0t is a silicon mold wired to an arduino nano that controls two pumps, a vacuum, coupled with three valves. The pump blows air onto three valves, each considered as an output, where air pressure, flow, and direction are controlled. Each output is connected to a void in the silicon mold, allowing it to bend and rotate according to the pressure that is in it. With this technique, a silicon mold can host casts of concrete and shape them around a controlled 360 rotation degree and a 90-degree bending angle. The inertia of the air trapped inside the mold keeps the soft silicon mold from bending all the way. When inflating and deflating one or more air pockets, we can reach all positions in the range of the deformed height of the silicon mold. A computation interface is created to control the performance of the b0t, with a real-time connection to Rhino through a geolocator. The silicon skin would be first pumped into the desired shape. A small hose linked to a concrete pump would fill the middle void. Air pressure will keep everything in place. Once concrete is dry, the system is deflated and air pockets are vacuumed, detaching the silicon from the extruded concrete. A separated system of fiber-reinforced silicon, controlled also by pneumatics, makes the mold move along what it has extruded. With this system of extruded filaments, we can divide a curved wall into different models and assemble them together. With metal reinforcement and a pour of structural concrete, we cast a formwork that is part of the final display, with no wood or rubber molds generated. The silicon skin can also inhabit a pattern that will repeat itself as the skin goes up, but never the same because of all the bending and distortion happening, which is why we worked on a pattern that could behave as a rainwater collector because of its morphology. This level of detail in regular concrete extrusions is time-consuming and hard to achieve, but with smart molds, one could achieve good results. To try to overcome the brutality of concrete and to achieve more plasticity and dynamic forms, the research process explored a wide palette of materials, trying to develop a bio-friendly concrete that cures fast, as the faster the concrete cures, the faster we can continue extruding. We looked into limestone and its fast solidification with water, mixed with sand, cement prompt, and a plastifier. The time of curing varies between 1 to 3 minutes, depending on the temperature of the water added. The catalyzation effect can also be controlled with citric acid, as it acts as a limestone stabilizer. Because of that important role, citric acid was replaced by a bioplastic tube made out of citric peels placed inside the silicon mold. It will help the cement both in its curing process, stabilizing its composition, and diminish its brutality through augmenting the level of elasticity of the structure. It also creates a neutral boundary between the human touch and the alkaline cement. Concrete, however, does not perform well in traction. Without any support or plastifiers, when we push an extrusion to its extremes, it cracks. Which is why we extrapolated a series of rules to: with no support, angle deviations should not exceed a 45-degree curvature. Generated support is assembled on site with the same tool. These sets of rules allowed us to create architectural applications. We envision a collection of b0ts working together in a swarm behavior from opposite sides, making it structurally possible to different filaments to meet at mid-center of the filament and behave like an arc.